Hello and welcome to Algebra, Unit 4-1, Lesson 5. This is the last lesson of your unit. So today's objective is scholars will graph and analyze transformations of piecewise defined functions. So now we're looking at transformations of different piecewise defined functions. So let's think about this. Cleo takes 3 one-hour classes at a community college. The graph shows the time she spends in each class. So you can see here, she has her first class goes from 8 to 9, 9 to 10, 10 to 11. Next semester, each class will start 1 hour later. How will this change the graph? So let's think about that. Let's try to graph this. I'll use green for this one. So if each class started an hour later, instead of starting at 8 o'clock, my first class would start at 9. I get to open here. My next class would start at 10, open here, and the next class would start at 11, go there. Okay, so that's what would happen if they each started an hour later. What about this? How would the graph change if she takes 2 90-minute classes that start at 8:30 a.m. and 10 a.m.? So she'd have an 8:30 a.m. class would start right here. Go for an hour and a half. And then her next class started at 10. Start right there and go an hour and a half. Okay, so that's what that would change to. So, now let's think about this. Uptown Sandwich Shop is increasing the number of bonus points by 2 in the shop's rewards program. How will the total points awarded for a $3.80 item change? So here's the current rewards program. Uptown Sandwich Shop rewards program. You get 1 point for each dollar you spend plus 5 points for each visit with no fractional points. So we can represent the functions for the rewards program with step functions. The original one, the one they have right now that we have over here, can be represented with f of x equals the floor of x plus 5. Or we could write that as f of x equals floor of x plus 5. And then, in that case, if we spent $3.80, it would be the floor of $3.80 plus 5. Well, $3.80 rounded down would be 3, so you get 8 points. If we were representing this with g of x, the new one, we would have the floor plus 7. So g of x gives us the floor of x plus 7, which would be the floor of $3.80 plus 7, which would give us 10 points. So all it would do is add 2 points for each visit. So that's the effect. It adds 2 points per visit. We can also look at this as a graph. If we graph these, you can see that the blue function here is shown on these blue lines. All it does is it moves each line up. Each line goes up 2. You see that each one just moves up 2. Well, now let's talk about transforming absolute value graphs. So what information do the constants h and k provide about the graph g of x equals the absolute value? Sorry, I actually had 2 of these. Y'all know where they should be gone. Absolute value of x minus h plus k. So we're going to look at this graph. This is the first graph we're looking at. G of x equals x minus 4. The absolute value of x minus 4 minus 2. And then we're going to look at the other graph. So here's, what do we see about this when we compare it here? It looks the same, except we have moved the vertex. So the vertex became 4, 2. And if we look at this next graph, x plus 5, x plus the value of x plus 5 plus 1, you'll see we have a similar thing. It's the exact same, so we've moved our vertex. In this case, our vertex is negative 5, 1. Notice our vertex is hk. Gives us the vertex of our function. Well, let's think about different things. How does changing A, affect our graphs? So we're now looking at comparing the graph of G equals 1/2 of X. So we see that right here. So you'll notice G equals 1/2 X is wider than the graph of F. F is being our parent function, f of X equals X, the absolute value of X. So when A is less than, ooh, that was the wrong direction. A is less than 1, it looks like it gets wider. So now let's look at this other version. A is negative and it is greater, its absolute value is greater than 1. Notice what happens. The negative flips it upside down. That's what the negative does. Negative flips it, remember? So that it opens down. And it is narrower. So when A is greater than 1, absolute value of A actually is greater than 1, it is narrower. Does that make sense? Because actually A would be less than 1, but the absolute value of A is greater than 1. It makes it more narrow, just like we saw in our parabolas. So now let's talk about, that was our vertical compression. So those are considered vertical compressions and stretches. So when we have G of X equals A times the absolute value of X, the constant A, so A is our constant, multiplies the output of the function. So if the absolute value of A is between 0 and 1, it is a vertical compression, which makes it wider. It's like we squished it down. When the absolute value of A is greater than 1, it is a vertical stretch. We make it narrower. We stretched it out. When A is less than 0, the graph is reflected across the x-axis. And that's where we flip it. So the value of A stretches or compresses the graph vertically. That's what that value does. Now let's look at a fully functional graph. So I have this full function. G of X equals A times the absolute value of X minus H plus K. So given that graph, we're going to graph G of X equals negative 2 times the absolute value of X plus 3 plus 4. So remember, the values of H and K determine the location of the vertex, and which also gives us our axis of symmetry. The value of A determines the direction the graph opens and whether it is a vertical stretch or compression. So let's talk about how we're going to graph this. The first thing we need to do is find our vertex. So we know our vertex is HK. So the vertex is HK, and in this case, that is negative 3, 4. Because remember, it is negative H. So it's going to be negative 3, 4. So I'm going to go to negative 3, 4, which is right here. That's my vertex. That's the first thing I'm going to do. That gives me my axis of symmetry. Next, I'm going to substitute in a value. I'm going to substitute in if X is 0. So I can find, well, it's actually G of 0. So G of 0 equals negative 2 times the absolute value of 0 plus 3 plus 4. So I have negative 2 times 3 gives me negative 6 plus 4, which gives me negative 2. So the next point I know the point 0, negative 2. So 0, negative 2 is down here. And remember, I have my axis of symmetry, which I'm going to just sort of give myself some dots here. Sort of see where it is. So I'm going to use that to create another point on the other side of my axis of symmetry that's 3 away. So in this case, I was over 3. So in this case, I'm going to go over 3 and put this point here. And that allows me to draw my function. So I'm simply going to use these points. to sketch my function. Okay, I hope that makes sense to you all. That is really how you're going to be graphing these given that option. Here is our concept summary. So transformations of the absolute value functions. So this is how we use all of this, what we went through. Adding a constant h to the input translates the graph horizontally. Adding k translates vertically. Multiplying by a greater than 1 is a vertical stretch. Multiplying by a less than 1 but greater than 0 is a vertical compression. And when a is less than 0, the graph of the function is reflected across the x-axis. It looks like this. This is the one we just did, and this is what the graph looks like. Okay, good luck with your classwork and mastery check.